Berlin, TU Berlin, and we talk about other half of the talk about half integral Erdős-Pósa. Please.
Thank you very much for the introduction. So thanks for coming to the talk and thanks for inviting me. So you may notice that the title is a little bit hedged. It's towards half integral Erdős-Pósa property for even dicycles. I'll explain that in a moment and why it's hedged. This is joint work with Sebastian Wiederrecht, who sits here, Stefan Kreuzer, and Kenichi Kawabayashi. A quarter integral version of this was accepted as stock. I'm going to talk about more recent stuff where we improved some of the methods and got a little bit better. And this is also like ongoing work for my PhD thesis. So let me begin with the basics. So I think 2 months ago, roughly, there was a talk by Sebastian also on the stock version. So I'm not going to give you the entire proof because there's already a recorded talk on this. I'm going to give you the details of why I think most of the proof works, and then show you what's keeping us from actually getting to half integral, and kind of explaining where the difficulty lies there and what the one thing is that we're currently struggling with and why we're struggling with it. So let's start with what Erdős-Pósa means. So Erdős-Pósa in 65 proved a very nice theorem, which many of you probably know. It says that there's some function f such that for any k and any graph g, either we find k disjoint cycles, or there's a small set of vertices a, small is f of k or smaller, such that g minus a is acyclic. So either we can pack a lot of cycles into the graph, or we can hit all the cycles with few vertices, packing and hitting. This turned out to be a very popular theme, and it appeared in many different areas, prominently in the graph-monoid structure theorem work by Robertson and Seymour, where we can pack planar graphs, but we're interested in packing cycles. And since we're not packing disjointly, I kind of have to introduce what it means to pack fractionally or half integrally or whatever. So we're going to say a class of graphs C has the fractional Erdős-Pósa property where the fraction is 1 over n if there exists a function such that for any k and all digraphs, since we're talking about directed graphs, either we can find k copies of graphs from C such that no vertex of the graph, the host graph, appears in more than n plus 1 copies, or appears in more than n copies, sorry, or there exists a small vertex that I can delete such that there's no copies of graphs from C anymore. So in this sense, Erdős-Pósa kind of had a 1 over 1 fraction, and in general, for the small fractions, we say if n equals 1, so if it's 1 over 1, we call this integral Erdős-Pósa. For n over 2, it's half integral. For 3, it's third. 4, it's quarter integral. We're not going to see much more than that today. So as I said, I'm just going to focus on cycles, so let me present you some of the basic cycle classes and what we know about them, especially about parodies. So we know about the undirected stuff that cycles have the Erdős-Pósa property, because Erdős-Pósa proved that. For even cycles, it's kind of folklore. I'm going to present a proof to you because I think some of the techniques, or because I know some of the techniques apply to what we do, and then it's nice to see why our structure theorem helps us do what we want to do. And odd cycles, surprisingly, do not have the integral Erdős-Pósa property, but Reed showed that they have the half integral one. So I could give you the counterexample why it's not integral, but this is kind of not super relevant to what we do. There's a different counterexample which we're going to encounter in a moment, because in directed graphs, all of the results are a little bit more recent. For dicycles, this was long conjectured. In the 70s, like very, very soon after Erdős-Pósa had the result, Younger conjectured that this should probably hold for dicycles. So I'm always going to say dicycles instead of directed cycles, digraph instead of directed graph. So I'm just so used to it. They show, Reed, Robertson, Seymour, and Thomas showed that this holds. So dicycles have the integral Erdős-Pósa property, and this kind of was the beginning of directed structure theory. So it's not just a nice result in the Erdős-Pósa sense, but it also kind of laid the groundwork for the grid theorem, directed tree width, and all that followed from this, at least in directed graphs. And for odd dicycles, there was a very recent result by Kawabayashi, Kreuzer, Kwon, and Ji, I think last year at SODA, and they showed that odd dicycles have the half integral Erdős-Pósa property. And here we can see the counterexample that actually interests me. This is a counterexample, or at least a way to construct a counterexample that odd dicycles have the Erdős-Pósa property. So if you forget about the orange vertices, you get a cylindrical grid. We're going to see this a lot. Cylindrical grid means there's some concentric cycles, and there's alternating paths going from inside to the outside, and then from the outside to the inside, and then a bunch of them. If you just look at the concentric cycles, you can see that these are even. They all have 6 edges, and through a little more analysis, you can see that there's no way to reroute any of these cycles to make them odd. Unless I give you back these orange vertices, then you can kind of change the parity, for example, of this edge to suddenly be even, and you get odd cycles. The only way to get an odd cycle is to use these orange vertices, so you kind of always have to breach this barrier of the outer cycle, and thus they all have to intersect. If you're trying to get several odd cycles, they have to intersect there on the outside. We're going to see this in a moment again, or rather a variant of it, but first let me tell you briefly why this worked. They used something that I'm going to call a quasi-apath theorem. So the apath theorem, the apath theorem, you may know this from MADA, basically says either you have a lot of paths going out from a set back into the set, or you have a small set of vertices that disrupts all these paths. There's also parity versions of this, and what they used is an even less specific version where you say, I have some odd walks that go back into my set, and if I don't have a lot of them, I have a small set of vertices that disrupts all of them, and if I have a lot of them, then I may have a lot of odd walks, but I may also just have a half-integral packing of odd dicycles. So there's like these weird hedging outcomes because they can't actually guarantee an odd dipath theorem, but this is enough for what they want. So maybe you can see here that no matter what happens, I either get an odd walk on the left, in the middle there's an odd cycle, and another odd walk, even though the path intersects, the walk intersects itself. So what about even dicycles? For even dicycles, we at least know they are not integrally packable, and the only thing I have to do is to put like a little bit of a parity break on these cycles on top. Now all of the cycles are actually odd. If I remove the orange vertices, if I put the orange vertices back, the same argument as for the odd cycles works again. So it's very nice that we're kind of using the same counterexample here. And the question is, how do we now show that these have some fractional packing property? And you could ask, well, is there some sort of apath theorem here, or a quasi-apath, or whatever? The problem is, no, there isn't. So you could, again, ask for, maybe you can disrupt a lot of these paths with few vertices, maybe you find a lot of them, or you find a packing of dicycles, but this does just not work. Down here you get an even path, but up here this is an odd path and an odd cycle. There's a bunch of odd cycles and an odd path. Even things just don't work well. In particular, in digraphs, we don't even know how to algorithmically, or we know that it's NP-complete, to find a given for 2 terminals an ST path that is even. That's just, we don't know how to do it, or rather it's NP-complete, so unless you can show that P equals NP, there's not much to do here. So that's not something we can do. So what do we do instead? We were able to show quarter integral by kind of showing a structure theorem. I'm going to present the structure theorem after I've proved to you that even cycles have the integral Erdős-Pósa property, but it's a lot more involved than using this quasi-apath theorem that the odd dicycles required. This is the stock version. This is from 23, and more recently we were able to show that actually you can improve this to third integral via some tricks, and we don't know about half integral. And if you ask me whether I believe it, it depends on the time of the day. It would be extremely strange for the answer to be third integral, because everything should be half integral, or I don't know, some power of 2. Third integral just seems wrong. But I also don't know how to get to half integral, so who knows? I don't. If you do, please don't. But I'll show you at least why I'm so weirded out by it. So let me give you a short proof of the integral Erdős-Pósa property for even cycles, and a little bit more about why directed cycles are weird.
So can I ask a question?
Yeah, sure.
So how many different proofs in nature for this original Erdős-Pósa?
For the first result?
Yeah.
There's a lot of very bad proofs you can do nowadays. I don't know if there's any more elegant proof. The original function, I think, is already k log k. and this is basically optimal. You can do a lot of stuff with structure theory. For example, the proof I'm about to show you, you can adapt to just show that cycles have the Erdős-Pósa property, but the functions would be terrible.
So if the non-structural approach, what are the proofs that are known so far?
I'm not quite sure. I would also not say that the original approach was particularly structural.
There's a new ball packing proof.
Oh,
Erdős-Pósa.
so the short and long of my answer is I'm not quite sure.
And is it also natural to why even the odd and odd? What about cycles of certain residue?
You're absolutely right. I forgot to say this. Several people in this group, I think, have both proven half-integral and integral versions of Erdős-Pósa properties in the undirected setting, where you get to label the edges of your graph with some group, and then make a condition on this has to be modulo whatever has to be 2 or something like this. Depending on what condition you set, you get half-integral or integral. But we know about this, or rather, members of this group know about this. I think almost everyone in the group had some part in one of either of these results.
So let me check what you just said. So for any residue classes, it's definitely at least half integral. That's what you're saying, right?
Yes.
I think so. Yes. I'm not entirely sure whether.
For undirected.
Yes.
Yeah. I think for the integral stuff you have to be not residue 1, right? Or not odd?
Yeah. That's right. So if you're
Which is kind of in line with the odd half integral thing.
this odd thing this generalizes to like you know, 2 more.
You can generalize the
We
Escher-Wall?
do have an exact character.
in some trivial ways you can generalize it, right? Like
Okay.
3 mod 6 is sort of just as
Okay. Yeah.
like other things like this you can get the same construction as the Escher-Wall. But yeah, it's always at least half integral.
Thanks for asking. I forgot to say this. So let me give you a proof that you can then generalize to a very bad proof of Erdős-Pósa. So I'm kind of splitting this into 2 parts. High tree width, I'm kind of assuming that everybody's fairly familiar with tree width. If not, we're going to generalize away from tree width in a moment anyway. So there's 2 parts I'm going to do. High tree width, so you may know the grid theorem by Robertson and Seymour. It says that if you have high tree width, then you can find a large grid as a minor. Let's just assume that we find it as a subgraph for now, or alternatively, I give you a wall. And this grid is, what I did here was a subdivision just to be like, okay, it can be some sort of grid. And the question is now, maybe in this grid I can find a lot of even cycles, but maybe it's possible to subdivide this grid such that everything's odd. I mean, this could be possible. Turns out this is not true. There's something called the theta property that says if you have some cycle and you take a chord through that cycle, which you can subdivide arbitrarily, then in this structure, in this theta, because it looks like a theta, you can find an even cycle. Sorry, I'm very pole on the dicycle stuff. You can find an even dicycle here for sure. Cycle. So that means that what I can do is I just take this grid, I pack these thetas into the grid, and then I find many disjoint I even wrote dicycles. Wow. Talking about dicycles, this does not work for dicycles, because if you take a chord or a subdivided chord through a cycle in a directed graph, only one of the 2 sides is going to be a cycle. So you can kind of fix parities, like this other side will have a different parity if the outer cycle was odd, but it might be on the wrong side. And then you end up with an odd cycle in an odd cycle, and that doesn't help you. So we can't use this either, but for the undirected case, this works. So this is high tree width. High tree width just uses one big theorem, and then you're done. Low tree width is a little bit more algorithmic. So we have a tree decomposition. You can kind of, if you don't know what it means, you can kind of take your graph and draw like bubbles around it such that the bubbles to each other are not very well connected. So if you delete any of these bubbles, you separate the graph, and the bubbles are not allowed to be very large. So you have small separators in the graph, and they're kind of organized in a tree-like fashion. Find your tree decomposition. Doesn't have to be algorithmic, but you could do this efficiently, or in FPT, I should say. And now the strategy is to find a bag somewhere in the tree decomposition that has the property that everything below it, if I just take all its descendants, these bags together are odd. But if I put this bag in there, then we get an even dicycle. even cycle. In other words, there's some even cycle that hits this green part. It must hit the green part because everything below it is odd. So what I do now, I just delete the guy, and then I repeat. And I do this until I can no longer find such a bag. I'm just going to do this exhaustively until the entire thing is odd. Now, if in this process I found more than k bags, then I end up finding a disjoint packing of k cycles. And if I don't, then I have a small hitting set because I've only deleted k minus 1 bags or something like this. So this is a very, I would say, rather elementary, other than using the grid theorem, proof of Erdős-Pósa for even dicycles, even cycles. And you can also use this for cycles. It would just be, the functions would be terrible. Don't do this. So the reason why I show you this proof in particular, this one is actually the one I'm interested in, is because the structure theorems, you may know, the graph minus structure theorem does give you a tree decomposition. And our structure theorem also gives us a tree decomposition. And using the structure we get from our structure theorem, you can use this as a template for the proof that ultimately, after you have the structure theorem, you get Erdős-Pósa, this time for even dicycles. So briefly to show you the structure theorem again, to get your reference, you may know the undirected global structure theorem by Robertson and Seymour. It says, if you have a graph and some t, then I can guarantee you one of these three things. I can guarantee you a kt minor, or you may have low tree width in t, which is also nice because it's also very structured, or you have a tree decomposition with small adhesion, which means the bags are easy to separate, such that every bag looks like this. And this means there are a few apices. These are things we delete. This is small in t. There's otherwise, the rest of the graph is embedded in some surface of fixed genus in t in a flat way. I'm going to explain flat in a moment. And there's also a few areas here that are allowed to be very bad, but they're not that well connected. And they're nice in a different way, but they're truly the terrible part. We want something similar, or we get something similar, although in some sense it's a little bit easier. So our structure theorem also says, give me a digraph, give me some k, and I either get you one of these three, a third integral packing of k even dicycles, third integral meaning cycles can share, or vertices can be shared by 3 cycles. D has low directed tree width. We're not going to talk about directed tree width, so just think of a tree decomposition. Or D has a directed tree decomposition with small adhesion. Again, this means the bags are easy to separate. Indirected tree width is slightly stranger, but it doesn't matter that much. Or where each bag looks like this. This means, again, you get to delete a few vertices. There are no vortices, and the rest is just embedded in the sphere, in something which we call an odd decomposition. In fact, this odd decomposition is so good, I'm going to explain what odd decomposition means later, that there are no even dicycles here after I remove the apices. Which means, if you think back to the easy proof, that instead of deleting the entire bag, you just delete these apices and separate me from the rest of the tree decomposition. This is how you would do the proof for Erdős-Pósa if you have this global structure theorem given to you. So let's get to the parts that I think are important for this to work, and what was difficult about working with directed graphs here. So what is flatness in undirected graphs? Flat means an embedding in a surface, and most of the drawing is without crossings. So on the sphere, this would be a planar drawing, except for a few areas where you have small separations that take me away from this nice cross-free drawing. They get to be small and they get to be non-planar because if I'm in the planar part, there's no way for me to build across through these parts because I can't route through two paths through here in a disjoint way. I just don't have enough vertices on the interface to this non-planar part. The reason why all of this works is one thing that I will show you that we do not have in the directed setting, and that is the two-paths theorem. This was proven several times, at least 2 times by Seymour. I think one of these is algorithmic, that's why there was separate citations. But the two-paths theorem is actually very simple and is very intuitive. It and it feels like it should hold everywhere, you're given kind of four vertices, A, B, B prime, and A prime, and they're kind of on the outside of the graph. I wrote they don't form a separator, so you can really imagine them to be on the outside. What you then ask for is some way to embed the rest of the graph in relation to these four vertices such that they're on the outside, like on the outer face, you can imagine, of a planar graph. And the two-pass theorem tells you you can either do this is the below, with a flat embedding. This is not planar, but the inside doesn't allow you to build a cross for these. Or you get a cross for these. Crosses are good for the global structure theorem because that allows you to build a KT, because crosses in a planar graph allow you to build a K5, for example. But the important stuff here is this actually lets you distinguish these two cases properly. Like either there isn't an embedding or there's something you can use. This is not the case in the directed setting. So why is this not the case in the directed setting, or what are the consequences of this? So one thing we get in the undirected setting is a flat wall theorem. You get the structure of the grid theorem here in a cubic version, and you get, with a few apices you have to sacrifice, a flat embedding of everything that's inside here. That's very important to you because this means this part of the surface is already nicely decomposed, and now you can go further from here and try to decompose the rest of the graph. There's also a flat wall theorem in the directed setting. This is by Giannopoulou, Kawarashi, Kreuzer, and Kwan 4 years ago. And what they do is they take some wall, and this is flat. And by flat, they mean the following. You either get low directed tree width, a KT butterfly minor, or this flat wall, including these things, these crosses on top. This counts as flat because they only have a few rows in the wall where this happens. The few in T, of course. But if you actually want to decompose a surface, this is very bad because this is not nearly planar. And something may go in here and use the cross and do some weird non-planar stuff. So this was not usable for us. Instead, we had to kind of redevelop the wheel of trying to figure out what flatness should mean. And this is where finally I get to what an odd decomposition is. So as in the other version, there's kind of a few areas that we need to consider. The first is most of the things are embedded in a cross-free way on the sphere in our case, and we even get a strongly planar drawing. This is stronger than just having a digraph that's planar, so cross-free. We also get to say on each vertex you can draw a line in the middle, and on one side there's the outgoing edges, on the other there's the incoming edges. Further than this, we also know for an odd decomposition that any even dicycle in this part of the graph that is decomposed has to touch somewhere outside of this strongly planar part. So we get even some control of how the even dicycles lie in our graph. The second thing is there's two types of disks now. There's some small separations in the same sense that small separations can be found in a flat embedding. In this case, there are directed separations of order 1. So you get to leave one vertex, and there's two strong components, one containing all the flat part I tried to embed, and the one whatever is above in the non-planar part. So you can kind of easily remove the non-planar part, and it's clear that I can't route two paths through here to form a cross. The last one is a little bit weirder. They're called small cycle sums. There's 3 of them. There's this digon here, so 2 parallel edges, or a transitive triangle, or this anti-directed cycle, plus some complicated conditions on how things are allowed to attach inside the non-planar part and outside the non-planar part. And it's all pretty awful, so at this part I'm just going to say there's a magical thing called matching theory, and if you look at matching theory, you can imagine this as C4 cycles that are glued together on planar bipartite graphs. So you have planar bipartite graphs, you identify some C4, you glue them together on the C4, and you get a new graph, and you keep doing this on C4s. So you can kind of imagine this tree-like structure at this point, where the small cycle sums lie and build up a graph that is in some sense still very simple because the way it attaches to each other is controllable. Ignore the matching theory part. This is the only part where I mentioned this. But small cycle sums are still simple. So this is what an odd decomposition is. This doesn't explain why they help, so let me explain why they help. So the first thing I already said, unless P equals NP, there is no hope to get a two-pass theorem in the directed setting. I gave a small example of a graph that doesn't have a cross, so there's no way to get from B to B prime and from A to A prime with two disjoint paths, but there's also no way, or no obvious way, to decompose this in a planar way in this disk. This example is very small, so maybe you can do something. Just an illustrative example. So this is pretty bad for us because we want parts of our odd decomposition to behave in this planar way. Most of our odd decomposition, the two smaller two-cycle sums and the directed tie-cuts are so small, or their interaction with the planar part is so small, that there's no way to form a cross. So this part is fine. The problematic part is that guy. So what about the four vertex guy? Here we actually have some very specific variant of a two-pass theorem by Giannopoulos and Wiederrecht from 3 years ago that says that if this guy had a cross, then the graph would contain a weak odd bicycle and thus an even dicycle. So we get an even dicycle, and now I've mentioned something else that I've had to introduce, weak odd bicycles. I'll need them later, so I have to introduce them here, but they're really very simple. So an odd bicycle would be just taking an undirected odd cycle and replacing each edge with an edge toward, or with an edge pair of opposite directions. So I gave here an example of a C3 and a C5 and a C7, and you can easily imagine how this goes on. In a weak odd bicycle, you can take any of these vertices and split them up into a path. That's just everything. That's all we have. This is a weak odd bicycle. You can do this for every vertex or just some subset of the vertices you like. It just has to be a path. It can't be like anti-directed. It really has to be a directed path. Briefly, why does this always contain an even dicycle? I'm giving here just the idea for odd bicycles, not the weak odd bicycles, but it's also true for them. The idea is just that no matter how you subdivide these guys, because you're not finding like something directly, it might be subdivided, it might be weak. No matter how you subdivide these guys, there is no way to avoid having an even dicycle. Like there's locally some cycles here, those might be even. In this example, I made this guy even. And if you try to fix this parity, if you try to make this local cycle not even, or odd, I should say, then you end up making some other cycle, in this case, the cycle completely on the inside even. So no matter what you do, you can't avoid having an even cycle here. These are very important graphs for this work.
When you say graph contains a weak odd bicycle,
Yes.
do you mean contains a subdivision of that, or?
Yes, I should say that, yes, sorry. Normally this is defined over butterfly minors, but I didn't want to introduce butterfly minors. But yes, I should say a subdivision of what we call bicycle. So we can avoid crosses at small cycle sums. Another thing we need to do is to kind of force things into out of the planar part of our embedding. So one nice theorem we found pretty early on was that in a planar graph, if you have an odd cycle and an even dicycle, then you can push the the even dicycle onto one of the two sides of the odd dicycle. This means, this is of course kind of a misnomer, but you can find one on one of the two sides. We call this shifting because you're kind of pushing an even dicycle in a certain direction, but of course the even dicycle doesn't get destroyed. It's just kind of a metaphor thing. We need this for planar graphs, but even more direly, we need this for, there's an even cycle, we need this for the odd decomposition, so this turns out to be much harder than proving this for planar digraphs.
What do you mean by described by odd bicycle?
If you take this to bound, if you take the cycle to bound two regions, then I mean literally the disk that is bounded by the, or the two disks that are bounded by the dicycle. One of the two disks contains an even dicycle, or the closure of them.
I see. So either inside or outside.
Yes. But even more interestingly, what we need to do is to decompose the rest of the graph. So we found some part that is already decomposed, that has an odd decomposition, and now we need to take care to actually decompose the rest of the graph to ultimately get our sphere that is mostly embedded with a few small cycle sums. And this is where the last variant of a two-path theorem comes in, and this needs a lot of requirements. So we are often in our proof in the situation that we find a large cylindrical grid, or really any sufficiently large cylindrical grid can be order 3 or anything larger, that is already embedded. For this we have a theorem. We call this the odd wall theorem. It's kind of our flat wall analog because we couldn't use the directed flat wall because it wasn't really flat. And inside we have some part that is not decomposed yet. So the first thing we do in our proof is do this odd wall to get some part that's decomposed, and then we have to further decompose. And here again, we can use something from outside that gave us a two-path theorem. But here note that this is a two-path theorem in the sense that we have a lot of structure on the outside. The two-path theorem has 4 vertices that have to be not a separator. And it's not really comparable to having a grid on the outside that kind of bounds an area and is already embedded. But still, this helps a lot. And Giannopoulou, Tidikos, and Wiederrecht last year showed that this either gives you a non-even decomposition in the middle, this is almost an odd decomposition, the difference doesn't matter here, or you don't get a cross, but instead you get a weak odd bicycle and thus an even dicycle. So the obstruction that somehow popped up here again was again something that gave you an even dicycle, which is nice for us because we want to find even dicycles. At this point, I have to tell you that we have to go away from walls because we can't even always guarantee a wall. So I'm going to go another level of abstraction away and say there's several types of structure we can find. I feel like I'm already running over time. Not quite? Okay. There are several types of structure we can find. The first is a wall. This is just going to be represented by a set of concentric circles. This is the nice case, but now we want to kind of split up this circle with a large set of paths that kind of go through the middle and we can embed them. The problem is that doesn't mean that on both sides we're going to get a cycle. If you remember the directed theta property, or rather the lack thereof, one side of these two is going to be 2 parallel paths. We call this a diamond, doesn't really matter, but this is why I call them diamonds up here. But this means that up here, we're lucky. So on the side that's not 2 parallel paths, we can keep going as we were. There's some set of concentric cycles. But on the other side, things get much worse. Suddenly we have to track that there's also something that interacts with these cycles that's not a non-planar part, but that's just a different part of the graph that's also decomposed. I'm going to be representing them like this because for the last few slides I'm going to talk about these. Just imagine that these cycles close at infinity out. What we're really interested in is the non-planar part that might be in here inside the diamond. This is one option, but it might get worse. So you might find something that goes backwards along these 2 parallel paths. And that we can't integrate either. In the middle of this, I'm going to try the laser pointer. In the middle of this, there's neither a diamond nor a set of concentric cycles that describes this area. So we have to remember that there was a diamond, but there's also these things going backwards, and also there's things outside, and in this case, all of the things outside are again cycles, so that's nice, but the middle is somehow even worse. There's a fourth thing which I want to present just to clarify something, or distinguish something. I also have refined circles. These are pretty new. Same idea as the refined diamonds, just that we have just a circle and things going backwards on the circle. So to go backwards on the circle, you kind of need to define an orientation, of course. But just to point out why I'm doing this, the first 3 structures I presented, circles, diamonds, and refined diamonds, were what got us to quarter integral, and circles and refined circles ultimately get us to third integral. At the end, I can explain why this is the case. This is mainly because you see two colors in the refined circles and the circles, and you can see 3 colors in the other ones. This will make sense later. Or I'll explain it later again. So what do we do with the diamonds? This is the part where it gets third integral, where we don't know how to get it half integral. So I want to decompose what's inside there. So if it's non-planar, there's probably a cross there, or several. And I'm going to call these here easy crosses because they're kind of easy to handle. In the sense that what I really want to do is I want to use that two-path theorem that said if you have a wall outside and some non-planar part on it, then you get an even dicycle. The non-planar part in the middle doesn't have to be too bad. It can just be a cross. I don't have to put an entire graph in there. So all I want to do here is to route these such that I get a cylindrical wall and a cross on it. This is not a cylindrical wall with a cross in it, but because these run in the right direction, for example, the leftmost run with the direction, or no, run downwards. The middle ones run with the direction of the two paths. The two parallel paths go to the right, and that cross also goes to the right. And the right one just goes up. So the middle one, I could just route towards the bottom using the paths. And the other ones, I can also route towards the bottom. In all three cases, I would just get a cross on a wall and use the two-path theorem. That's ultimately what we want to do. But there might also be a not so easy cross that goes backwards against the direction. Here it's easy to see that I can't really route this. Somehow these paths are like in the way of each other. But there is something I can do which is pretty neat at this point, and that is I can reduce away from all this complicated structure and just take one of these paths, one of these cycles, and the cross, and give you a weak odd bicycle. This is not so easy to see, not even for us. It took us a while. So you might not be able to see it here. Here's what here's basically depicted what I said. I took one of the cycles, one of the paths, and one of the crosses. And on the right, I tried to depict this in a way that it looks like one of the weak odd bicycles I showed you. There's three cycles, and each of the three cycles intersects the other one, but no three of the cycles intersect in a common endpoint. And each of the cycles intersect in single segments. So you end up getting actually immediately, without moving anything, a weak odd bicycle. But, and this is the part where the colors were important, I have used three different parts of the structure instead of just a wall and a cross. And this is important because I might have to move more than one cross with this infrastructure. It might be that this is the last part of the graph that is non-planar, and I somehow have to embed this, but it turns out that that I'm still searching for, I don't know, 40 even dicycles, and I have a lot of crosses there, and I need to show you that these crosses give me even dicycles, because that's the only option that's left to me. I can't delete enough to actually make it all go away. I have to do something with these crosses. So now I'll show you where it gets third integral. This is the last slide. I'm gonna have to reuse colors here to be friendly to the colorblind. I guess Linda's gone now. And the idea is that each of the colors, orange, green, and blue, represents one of these weak odd bicycles. So the first one I'm gonna show is already one that uses a cycle, a path, and a cross. And this may be one color, but these guys intersect. The cross intersects the path intersects the cycle, and the cross intersects the cycle. So this is just to be clear that these are not disjoint in any way. The second one lays over top. I'm still in the same infrastructure, so I kind of have to choose them concentric. I'm choosing the second cycle further outward, the second path further outward, and the second cross is just one of the crosses that I found that are pairwise disjoint. The last one, again, one cycle further outward, one path further outward, and another cross that is disjoint from the other crosses. And now is the problem, everything that I drew here that's not like indicated as not crossing is actually touching. Everything outside here is part of the infrastructure that is already embedded. So I can't do anything here. This is planar. This has to, if the colors or if the paths intersect each other, these have to touch vertices. So this thing here, where there's a blue thing touching, a green thing touching, an orange thing, is extremely bad for me because I cannot disentangle them easily. Here, it might be that the even dicycle I find uses every single part of this and meets on that vertex, and this is third integral. The problem here, and this is the thing with the colors I said earlier, is that we have two types of infrastructure. We have the cycles that form the diamond, the paths that form the diamond, and we have the crosses. The paths intersect the cycles intersect the crosses, and the crosses intersect the paths, But all of these things in and of themselves are disjoint from each other. So the paths are disjoint from each other, the cycles are disjoint from each other, the crosses are disjoint from each other. But that still allows them to, if I choose badly, or if I'm very unlucky, that still allows a path and a cycle and a cross to intersect. I said earlier that the the 3 colors that I had for the previous infrastructure for quarter integral was the reason we got quarter integral. We had cycles, paths, and another set of paths going backwards, and then you had crosses, makes 4 quarter integral. We reduced this to 2. That's why we're third integral. We had to refactor some proofs for this. They actually got a little simpler. But the problem is that we can't get away from this. You can't get rid of diamonds because one side is not going to be a dicycle. And I like this picture, so I decided to leave on this. And I hope I've answered all the questions I've brought up, but please ask some if you have them.
Thank you. Any questions?
Oh, sorry.
I was just gonna ask, so this is the only place you get 1/3.
Oh, yes. I should have pointed this out again. This is the hurdle, the only hurdle.
Yeah. And so if you've got a large third integral packing here, so yeah, initially I guess it could be third integral. Is it clear that you can't refine the like just throw away some things so that you get rid of the
Throw away some of the cycles.
just get a smaller packing?
We thought about doing some kind of Ramsey thing.
Yeah.
It feels like you could probably do some sort of Ramsey thing, but we couldn't figure it out.
Okay.
I should point out that I kind of lied here. This very specific situation I can solve. There's, using all the shifting lemmers, there's some fun thing to do here. The problem is that I simplified some of the structures so that it might intersect more complicatedly. And the crosses also are not as behaved as I depicted them. So these can go into the structure and back out and cross several times.
Okay.
It might even do so in a way that changes the number of. So if you move in a little bit, to explain it in a different way, I chose different cycles at different depths to move the crosses, right?
Okay.
So if this cross ends up going in here, crossing once, going back out, crossing once, and landing on some cycle, then it might have crossed twice, and thus is not actually twisted. It's not actually a cross, in the sense that it doesn't. Let me actually just paint it. So the infrastructure might look like this, but because I'm using different parts of the infrastructure, so maybe this layer here, to move different crosses, it might be that a cross goes, I want this, this, and this, and the other part of the cross goes across here, then meets this part of the infrastructure, so this is the part of the infrastructure I want to use, here it crossed twice, and with respect to this is not actually non-planar, because I can untwist this. If I'm just looking at this part of the embedded part, I can just turn them around, this planar, so the two-path theorem would tell me, oh, this is an embedding, nice. But it might end up being a cross like this. So this kind of thing can really mess you up because you don't know how these paths behave. So a lot of what we try to do is like cleverly choose different parts of the infrastructure, but this does not always work. Or at least I don't know why it would always work. I have a lot of arguments that get rid of some cases, and then there's a few left where I'm just not sure what could be done. Not sure if that answers your question.
It helps a bit. Yeah, I don't see the picture clearly enough to know to really understand it.
I'm sorry, there's
No, it looks like there's a complicated thing going on.
yeah, it's sadly.
That is difficult.
Somebody else was.
I thought there was somebody who was trying to.
I have a non-math question. I wonder if doing research in this direction taking drawing classes because both you and Sebastian has like very nice pictures.
I had to learn a lot. My drawings used to not be that good. I used to do everything in ticks, but this just takes less time for the amount of drawings you have to do.
So you also have algorithm, right?
Yes.
And is it like FPT or is it, can you say what velocity, running time?
I can guarantee to you that it's XP.
XP, I see. The exponent increases.
Yes.
Really? For
I have an argument, yes. The factorial thing I told you about is XP.
For because of third
It's
integral.
ugly, yes,
Yeah,
but
Oh. So the exponent increases by the number of cycles you're trying to
Yes.
find?
definitely. This is another thing where there's like one hurdle, and if we get the hurdle, we have FPT, but currently stuck.
And also I'm curious about this quarter integral LP, and then you have a 1/3 the third integral LP. Were there certain cases where are there any other combinatorial problems where
None that I
these are
know
known to
of.
be
That's
like-
why it would be strange if it's third integral, because why would it be third integral if everything else is like powers of 2? I don't even know of anything that's properly quarter integral.
So if some LP has like third integral as well as quarter integral, there might be certain features that say something.
That I sadly don't know.
All right. Any other questions? Or? So if not, let's thank the speakers.